Hi there. So I'm going to start off by teaching you how the sarcomere works and what it is. So first off, this right here is a sarcomere. Now, what the sarcomere does is it is the smallest part in your muscle that uses calcium to contract a muscle fiber, and then a muscle, like it builds, but this is the smallest part of that breakdown. The measurement of a sarcomere is from Z disc to Z disc. So that's one sarcomere length. What you'll find in a sarcomere is there is an H zone, which is where you will find that that's the space where the sarcomere contracts and comes closer in together, or where it goes further apart until it's back to its normal length. The line in the middle of the H zone is called the M line, and on either side of the Z disc is something called the I band, and in the same area as the H zone is our A band. So with our I band, we'll find it's a light area. With our A band, we'll find that it actually will be darker when we look at it through a microscopic view. So with a sarcomere, there are multiple parts. First, we're going to talk about these two proteins right here in dark blue and red. The one in blue is what we will call nebulin, and the one in red is titin. Now, attached to nebulin is this little G protein, just actin, this actin molecule that's called globular actin. So one of these little guys right here is called G-actin or globular actin by itself. But if we were to combine them into an alpha helix type of form, so when they cross and connect, like an alpha helix, it is then called fibrous actin or F-actin. Now, these actin have these little head areas where they hold ATP and are where the myosin heads can attach. No, scratch that on the ATP part, I think. Yeah. It's just the part where the myosin heads can attach. And there's a good reason for that, and I'll explain it later. So each G-actin has a little area where the myosin heads can attach. Now, what's preventing those from attaching is something called tropomyosin. Now, tropomyosin is this filament that covers up to 7 to 8 G-actins, or the length of one actin. And like I said, it's there to prevent the myosin heads from attaching to our G-actin molecules. Now, the reason that our myosin heads need to attach to our G-actin molecules is that when calcium is introduced to the muscle, it needs to be able to contract. And what those myosin heads are going to do are they're going to attach to those F-actin molecules, and they are going to pull them in closer. So these two nebulin proteins are going to come in closer and contract, therefore contracting the muscle. And we don't want our muscle contracting all the time, so our tropomyosin is making sure to keep our muscles relaxed when need be. But what's going to cause it to react? So when you have troponin, you have three little molecules. There's troponin T, troponin I, and troponin C, and that just mentions where they attach. So troponin T, that's going to attach to the tropomyosin. We have troponin I, which is going to attach to the actin, and troponin C, that is going to attach to the calcium. And this has 2 high affinity points and 2 low affinity points. So there's 4 points, 2 are high, 2 are low. And this one right here is going to be the main thing that causes the tropomyosin to be removed. So when calcium is introduced to the sarcomere, it's going to attach to the 2 low affinity points within the troponin on the calcium of troponin C, and it's going to then pull back this tropomyosin, pull it back and bring it to the back, leaving that F-actin open and available for our myosin head to attach to it. And the whole thing together is called myosin. Now, myosin is attached to what I had mentioned before, titin. These proteins, titin, have myosin on top of them. So troponin causes tropomyosin to move back, and that allows for myosins to attach and cause the cross-bridge cycle, which I will draw and explain here in a sec. Alrighty, so now we're going to look at the cross-bridge cycle. And first, we're going to start off with the fact that we have a cocked myosin head that has ADP and inorganic phosphate separated from each other, but they are together. It is cocked. It is now rest. Now, we are going to introduce calcium to the system. And when we introduce calcium, the myosin head is still cocked, going to attach to the nebulin protein or the F-actin molecules right there. And while it is attached right there, it still has its ADP and inorganic phosphate, but it will start to release heat. And when it releases heat, that will then cause for the ADP and the inorganic phosphate to be then released and then cause for it to, the myosin head to go down into a 45-degree angle. And we call this uncocked. And this movement right here is called a power stroke. So we've now initiated the power stroke. We are uncocked. There's no ADP or inorganic phosphate. What is the body going to want? It's going to want to replace those ADP and inorganic phosphate to bring it back to cocked, because if it stays here, we'll be contracting forever, and that's not good. So it will then introduce ATP to the system. And so it'll still be cocked, but now we have ATP, which then will go through something called hydrolysis. And by doing so, we will then go back to a detached myosin cocked head with ADP and inorganic phosphate separated and where they needed to be until calcium is reintroduced and the system starts all over again. So that's a cross-bridge cycle. That's the reason why our muscles contract, is because of all this action right here. And we do know that if our muscles do contract, then there will be a raise in body temperature because the energy that's being released is heat. So that is the cross-bridge cycle. And then I will move on to where in the world this calcium comes from and how it arrives to the sarcomere. Alright, so to continue, I was going to explain where the calcium comes from. So what we're going to talk about is, so let's start at the very beginning. So we're in the axon terminal, and right here is a voltage-gated sodium channel. And so what this is going to do is it's going to let sodium flow in, and when it flows in, it's going to cause action potentials, which will then cause the voltage-gated calcium channels to open and cause action potentials that also release calcium in. And the calcium is then going to attach to these little green things called snare proteins. And they're going to bring these vesicles filled with acetylcholine, ACH, down to the end of the axon terminal for exocytosis. And then what the acetylcholine is going to do is acetylcholine is going to attach to this ligand-gated sodium channel, and that will allow sodium to flow in to the sarcoplasm and also cause action potentials all the way to other voltage-gated sodium channels. And then that will cause that other one to react. That'll cause that other one to react. So all these voltage-gated sodium channels are going to keep going down, down, down until they reach the DHP receptor. So I really didn't label this. So this is ligand-gated sodium channel. And so now we're going to reach the DHP receptor. And none of these are scaled to size per se, because I can't draw very well. But the DHP receptor, what it's going to do is, DHP receptor is also known as ligand-gated calcium channel as well. So when this action potential happens, the calcium is going to attach, and it's not going to come through. That's the weird thing about this DHP receptor. It's not a way for calcium to get in. So instead, what it's going to do is it's going to cause this ryanodine channel, which is attached to the sarcoplasmic reticulum and also chocked full of calcium. What the DHP will cause is for the ryanodine channel to open within the sarcoplasmic reticulum and release calcium into the sarcoplasm. And then that will then attach to the sarcomeres, which are smaller and are within the sarcoplasm. It's going to cause the cross-bridge cycle to happen, and then we will get contractions, continuous contractions. Now, our body doesn't want to stay like that, because then it could cause something like spastic paralysis. So what we have is this little pump right here called the circopump, which is it's going to take all this calcium that is now in the sarcoplasm and pump it right back into the sarcoplasmic reticulum. Now, it's going to be slower than our ryanodine channel because this one goes with the gradient of calcium, while the circuit goes against the concentration gradient of the calcium. And I forgot to mention, but this cascade down into this little divot, this is called a T-tubule. And it is within the ECF. So there is the extracellular fluid is where it's getting the calcium from to cause this gate to open the other one, but this calcium never goes into this. It always stays out here. Now, though we have this slowing down, we still have the DHP being caused by these action potentials to open the ryanodine. So even if we're causing this to go in, that doesn't stop contractions. What does help stop contractions, because this does help, but it's not going to stop unless this thing called an acetylcholine, I'm just going to write it like this, esterase, comes in and eats up all of our acetylcholine. Once that's done, we lose all of our action potentials. So then it stops producing more. The circuit now can just catch up, get rid of what's left of the calcium that's within the sarcoplasm, put it back in the sarcoplasmic reticulum, and our body will become relaxed. So that's part one of the essay. I explained how the sarcomere looks and functions, how cross-bridge cycle is part of that, and where the heck we get the calcium in the first place. So yeah, that's part one.